Hi everyone, let's start with the today little problem. Problem number 2328, number of increasing paths in a grid. So let's read the problem statement. You are given an m into an integer matrix grid where you can move from a cell to any adjacent cells in all four directions. So let's say like we are at this cell, so we can go either in the right direction, the left direction, we can also go upward and we can also go downward. Okay, so that is the meaning of this from any cell to any adjacent cells in all four directions. So we need to return the number of strictly increasing paths in the grid such that you can start from any cell and end at any cells. Since the answer may be very large, we need to return it modulo 10 to the power 9 plus 7. And two paths are considered different if they don't have exactly the same sequence of listed cells. Okay, so let's try to understand the problem statement using any of the example that is provided. So for example, let's take this input. So here we have been given 2 into 2 matrix and the elements are 1, 1 and 3, 4. Okay. Now let's say like I started my DFS from this place. Okay. So paths with one lengths are 1. Similarly, let's say like I started from this place, I started from this place and I started from this place. So that's why paths with length 1 are 1, 1, 3 and 4. Okay. Now let's talk about the path with length 2. So let's say like I started from this place, then definitely I can go downward direction. I can't go upward because like that is out of bound, and I can't go left and right because in right one if you see like we have a number that is equals to this one, and we have a strict restriction like we need to return the strictly increasing paths. Okay, so we can go only in the downward direction. We can't go there. Okay, so from here we can go to this one, and from this place also we can go to this. Okay, so here if you see like the path is 1 2 3 and 3 to 4. If we just perform the standard DFS from this index that is having value as 1. So here if we see like this is also a path, and this completely also a path, so that's why within the path of length 2 we have one path 1 2 3. Okay, similarly let's like I started from this place. Let me clean it quickly. I started from this place or this cell. Then from there, I can't go into the leftward direction because the element is equals to the current element. Okay, definitely I can't go upward in the right direction because this is out of bound. So I can go into one possible places downward one, and that is satisfying all the constraints. It's a valid cell and its value is greater than the current cell value. So we have one more path, 1 4. Similarly, like if we start from 3, you can only go to this right direction and you would have this path 3 4. And if we consider the path with length 3, then I can go from this place to this place and from this place to this place. Okay, so that's why paths with length 3 we are just having one path on 3 and 4, and total number of path is just the summation of all the paths 1 3 and 1 2 and 3 4 1 2 and 3 length, that is having 4 value plus 3 value plus 1 value. That's why the total value is 8. Now let's try to come up with an approach to solve this problem. So let me quickly jump to. So yeah, we have our matrix as 1 1 3 and 4. This is just a 2D matrix that I am just representing here, but let me make it more precise. Okay, so this is our original matrix. Okay, and we just need to find total number of increasing paths. Strictly increasing paths. So this is our problem statement. Okay, so we have this matrix. So to traverse this matrix, we have two standard algorithm, that is a DFS and PFS. Now, if we see here, like we just have to find the path. Okay, so from any particular cell, what are the possible cells that I can visit? So we should stick for our column statement to DFS algorithm, because here like we have to perform it in a depth-wise fashion. So let's say I started from this one, then I can go to this three, and from this three I can go to four. So this entire path, let's say like we have more elements here, and from there, from four we can decide to go to the next possible path. So we can stick to this DFS approach. Okay. Now we finalize the approach. Now we have to take care of multiple things. Like while performing the DFS, like we need to take care of multiple things. Okay. So the first constraint would be like the element or the next cell from any particular cell, whatever is possible to visit, since it is allowed to visit all the four directions. Okay. And we need to ensure like while going to the next direction, whether it is a valid cell or not. Check for valid cell. If it is out of bound, then definitely like you can't go into the leftward direction. Okay. And also we need to take care like the number or the cell to which I am currently going from my current cell should satisfy the constraint, like the next value should be greater than this one. Now in our DFS, like yeah, these are the constraints that we need to take care. Now we'll just stick to the standard DFS approach to solve this problem. So let's take one example to understand the DFS properly. So I'm just taking a binary matrix. Let's say like we have been given this binary matrix, okay, and we need to perform the standard DFS approach. So for DFS one, like we need to consider like from this particular cell, let's say like I can go to all possible directions, but we know like we can't go upward and we can't go into the left direction because like these are not a possible valid cell. And in the right one also, if you see here, like this cell we can't visit because it is containing zero. Okay, so we can go to the downward one. So from this place, we are just going downward. We are having this one again, and from this one here we can take a call, and we'll just see we can go here, and from here like we can take a call either to go take this path or take this path. Let's say like I decided to go with this path, and after that I ended up there because from this place I can't go any other places. Okay, now we'll start rolling back. So from here, I think we don't have any other path to visit. From here also, like we don't have any other path to visit. And from here, like we have one more path to visit, and we'll just explore that one, and we are done with the DFS. So let's do a quick numbering. So one, two, three, four, five, and then six. So we have followed the same order. One, then we go to this one, four, five, and then six. So this is a standard VFS that we just discussed. So we'll just try to utilize this standard VFS to solve our problem also. So in our standard VFS also, like whenever we are making a call to check whether for the next possible cell that I can visit from this cell, that it is valid or not. So while doing the validation, we need to ensure the same constraint that we have just discussed before, all these three constraints. And after that, like as soon as like we find it's a valid cell, then we just need to, well, let's say like we have a variable and we see like the next cell that I can visit from this parent cell, it's a valid one. Then I will just increment its counter. And as soon as we are done with one possible DFS call from any particular cell, then whatever total submission we have, we will store that one and we will start doing the DFS from any other cells. So let's say like I started from this place. Okay. Then from here, my current count value is 1. From here I came to this place, and from here I came to this place. Okay, so the total summation here we would have 3. Okay, Similarly, like we would start from this place. Okay, let me change the color of this pen. We would start from this cell. Okay, so from here, like we can go to this path and this path, and yeah, that's all like we can go. So we'll just increment our count also. 3 plus 2 5. From here, if we start, we can go to these places 3 and 4. So two length we have, and from 4 if we start, we can just go to one places only, that is 4 only. So if we do the total the method is 8. That is our expected output. And the parts that we have explored, the first three length path is 1, 3, 4. This is one part that we have explored. And then we started from this place. Here we have covered 1 and 4. Then we have started from this place. From here, like we have covered this path. And from 4, like we have covered this path. Okay. So here if you see, like we have three different paths. 1, 1, 3 and 1, 3, 4. That's why for this one we have 3. And here if you see, like we just have two paths. 1 and 1, 4. And for this 3 4 we just have two paths, 3 and 3 4, and for this 4 we just have one path, that is this 3 2 2 1, total is 8. Hope you understand the approach. And now let's just discuss the time and space complexity of this approach. So here if we are just performing the standard DFS, but one catch is here, like in a standard DFS, whenever like we are visiting any cell from any possible DFS path, then that cell we don't process next time, and we ensure that one using the visited array. So let's say like here we have this 1 1 and 3 4. Okay, so through one call, let's say like I started from here, like I covered all these three nodes. So the next time, like I will not allow to visit these cells, because I will mark them as a visited one, and I will just explore this path. Okay, otherwise like I would stuck with some infinite loop. So again from this one, like we are doing the same thing. From here also, like we started traversing this 4, and from 4 also, like I can traverse to like let's say like currently it is not possible to travel to go back, but here like you can understand, like if we don't take care of this thing, then we could stuck with some infinite loop. For example, let's say like I have 4 5, or we will just do the unnecessary iteration. Let's say like I started from 4, I came here, definitely from here also, like I can go here. Let's make it 8, I came here. Okay, so we are done, we have visited all the paths, and we will start from 5 also. Then I will traverse this 5 7 and 8. Definitely we can't visit 4, because it is not satisfying one of the constraint, that is this last one. Okay, and from 7 also, like if we start, we will just visit 8 also. Definitely from 8 we can't go upward. Okay, so if you see here, like from each possible, for each possible cell, whenever we are choosing, like we are allowed to try all the matrices, try to visit all the matrices, to ensure that one, like we don't process the same duplicate element multiple times. Let's say like from 7 to 8. From 5, like we have started 5 6 4 5 7 and 8. Okay, like we have visited this path. And from 7 also, like if we start, I know like only one path would be possible. Okay, so at any point of time, what we can do, like we don't need to process it from here again, because we already know the total number of part that could be possible from this place is one only. From this 7 we can go up to 8 only. So what we can do here, like we can do one small optimization. Otherwise, like we would do the unnecessary processing each of the time. So to avoid this one, like what we can do, we can use the memoization technique. As soon as for any particular cell, let's say like I've done the processing, let's say like for 5 I have already done the processing. Okay, and we store its count as 3. Okay, and somehow like I again came to this 5 through any other path. Okay, or through any TFS path. Let's say like I have 3 here, and from 3 here also I came to this 5. Okay, then we already know, like for this place, like the TFS, the path or total number of possible paths could be 3 only. So we'll just store the state here, so that we don't need to do the unnecessary processing here. So if you perform the optimization memoization technique, the time complexity would strict to n into n. And space complexity, like we have to perform the memoization, we would take n into n. So let's say like for this example, from 1 1 we are start from 0 0 we are starting. Let's take one example to understand why the time complexity is 1 1 3 4 we have. Okay, and let's say like I have a matrix. I'm just representing this 2D matrix here. I will just populate its value. Let's say like the default value is 0 0. Okay, so whenever I am starting from any particular cell, let's say like I'm starting from just 0 0. Before its corresponding cell, I will check whether we have already processed it or not. So if it is 0, then it simply means like we have not done the processing yet. So we are good to go ahead and do the processing and store the result. So what I will do, like I will traverse here and from this 3 to 4. So for this one, like we know its current value would be 3. Okay. Next, in my iteration, let's say like I choose this cell to do the processing. Okay. From here also, like we see like we have not done the processing yet. So we are good to go ahead and do the processing. So I will go downward 1 and 4 only. So I will just update its value to 2. Let's say like I started again from here. For the third cell, I will start processing, and from this here, we see like what are the total cells that we can visit. So I can visit up to this 3 and 4 only. So I will update its cell corresponding value also with 2. And from 4 also, like I can't go anywhere. So I will just store it at 1. Okay. So this is a trivial example we can say. Let's change some data to understand it properly. So let's say like instead of 4 here, we have 2. Okay. Yeah, let's take this example. 2 1 3 4. So when we'll start from this 2, okay, definitely at this point we have not processed that particular cell. So as soon as like we'll done, so definitely like this will be the path 2 3 4. So we'll update its value by 3 because we know there are three paths 2 2 3 and 2 3 4. Okay. Now for the next cell, I will start from here. Okay. For this cell, if we see, like we will start making the recursive call from this one. Let's say like I can go to this two. Okay, so we have made one recursive call. So earlier call was from one. Now a call would be from two. But for this two, we already know the result. That is already stored there. Okay. So what I will do, like whatever its current value is, I will just take that one instead of doing and processing the entire thing from here. From scratch, we already know its value. Okay, so what I will do, my count would be like we already know its summation, it would just return me its corresponding value of 3, and for this one current account is 1, so 1 plus 3, that is 4. So here if you see like we have stopped the unnecessary processing. As soon as like we have wasted one cell, we have processed for any particular cell, we will start utilizing the result of that one. We will stop the unnecessary processing. Again, let's say like you came here from this 3, you can go to 4. Okay, and for 4, let's say like I don't have any result, so definitely like I will do the processing and I will store its result to 2. And from 4, definitely like I can go nowhere, so it would be 1. So at any point of time, I will just process n into the entire matrix. And as soon as like for any particular cell, if we have a cell ready and from any possible path, TFS path, if I'm visiting that cell, I will just utilize the element or the result that is already stored there. So let's try to do the quick coding for this one. Hope you understand why the time complexity is order of n into m and the space complexity is order of n into m. So let's try to code the solution. So we understand like we have to implement standard TFS with the given constraint. Let's try to implement this one. Let's calculate the size of the matrix first and store it in some variable so that we can utilize it whenever it is required. Now we understand like we should do some optimization. So by default, like if we are implementing any standard TFS, we have a visited matrix. There we used to store and check like whether we have already processed that cell or not. The same listed kind of matrix we can utilize here also. So let's use the same naming convention. So there we have a listed matrix of Boolean nature because we just store true and false to ensure like whether we have already listed that cell or not. Here I will use a listed matrix of integer type so that I can store the path if you have already processed that path. So let's start iterating. So by default, the initial value of all the cells that is present in this state matrix is 0. So we don't need to do any initialization explicitly. From here, like we can start calculating our result. So let's say like I have my result as 0. Okay. And now I can start calculating the and start populating the result. So here, let's first try to make the standard TFS form. So there I should pass the required attributes like I, J, and this listed. Okay, I will just implement this method and I would store it. Since we have to perform the modulo operation also, that's why I'm not using plus equals to operator. Because we can perform the mod operation. Let's say like I have this mod variable defined. I'll just define it. And since the result could be very large, so I will just apply the standard modulo operation here. Okay, let's define this variable. Private static int mod equals to 10 to the power 9 plus 7 1 2 3 4 5 6 7 8 9. Okay, now we are good here. We have defined our mod. Okay, now we are making the recursive call and we can simply return result from here. Okay, now let's implement the method that we are calling, this TFS based method or this TFS method. Its nature would be of integer type because I am returning the total possible path whenever we are processing for any particular cell. Okay, so that's why you have defined it as integer. I'm just taking the required parameter, the signature that using which we are calling this method. Okay, now we have our signature ready. Let's try to implement this method. So let's do a quick lookup. If already registered, then we don't need to do any processing. We can simply return the result directly from the standard memoization technique we are implementing here. Okay, and if it is not, then definitely like we need to do the processing. And from any particular cell, the possible cells that we can, although if we want, we can make it static and outside of this method at global level so that for each method call we are not creating this array and doing the initialization with these values. Let's keep it in this method. So these are the all possible directions from any particular cell that is currently x and y I can go. Okay, just writing it in such a way like you can easily scale the solution for 8 direction also, you don't need to do much changes. So I'm just making a call to check whether it is possible to visit or not. It's plus okay, y plus okay. So all the four possible directions we are trying. So from any particular cell, like I can go downward, upward, left, and right. So these are the possible directions that I can go. So I'm just applying that one. And after that, like we have this grid. Okay, x, y. Wasted we don't need to take care, that has been taken care here, and we just need to update it. And after that the current element, because at any point of time for the possible cells that I can visit from any particular cell, we need to ensure whether we can visit it or not. Okay, and I'm just implementing, let's name it path instead of, let's create this variable path equals to 1. Okay, for this individual cell the path is 1. And yeah, we are just performing this. Okay, we don't need to do it in this fashion. What we can do, because if it is a valid cell, definitely like we need to make a call here. Yeah, if you see the signature, like we are passing wasted, not grid. Okay, don't confuse the signature of this is valid method with this GFS method. Here we are having first a 2D matrix, then X and Y, then again a 2D matrix. Okay, so we have these things ready. Let's apply the standard module operation here also. And so I think like we have covered and applying it, and we are closing it properly, so we are good here. And after that, like we should return for this method the total number of paths that we can do. So here we have introduced one method is valid. I'm just trying to break the code into modular code so that we can reutilize the code and it's a standard practice to make your code as modular as possible so that it should follow proper design pattern and principles. And it's also become very easy to do the unit testing and debugging because we know the responsibility of each of the method and we can easily take a call. Okay, so here we are having this signature. Okay, so we are taking the grid in this grid. Okay, and after that x and y possible cell x and y coordinate. Okay, and this grid value that is the current value. Let's calculate the n file and the standard format I will use that I follow. I'm just doing a quick boundary check. And this grid value should be strictly greater than current element. And now I think we are good. We can try to run our code and see if there is any compilation issue. Okay, I think like we have included more zeros there. So okay, still it's complaining about this one. So one, two, three, four, five, six. Okay, now I think we are good. So you see like our code is working as expected. Now what we can do, we can try to run our code on some another input to ensure its correctness. So here if you see like we have missed one thing. Like while returning the path, we are not doing the optimization, the memoization technique that we have discussed. So we should store this so that for the next call, we don't need to do the processing again and again. Okay, now I think we are good. We have included the optimization technique also. As soon as like we are finding the result, we are returning it. Otherwise, we are going to process it and storing the result. Now let's try to submit the code and see. So yeah, the solution got accepted. Hope you understand the concept of standard DFS and how we can utilize the standard DFS technique to solve this problem. So yeah, that's all I have from my end.